Okay, Pa. So look here, this is a small demonstration on oscillation. Then after that, we will move on to the various types of oscillations. Okay. So you could have seen in that board I had drawn three curves. Okay, those three curves were nothing but different types of damping of that video. Okay, they are critical damping, over damping, and under damping cases. Okay, so that is what today we are going to discuss. Okay, so shall we move on? Get started. Okay. Okay, Pa. Yeah. Okay. So look here. In the last class, we discussed about the theory of damped oscillations. Correct? That is, if you consider a mechanical oscillator which is inside a inside a bucket containing water, and it is when it is set into vibration to and fro motion, then we analyzed and we found how the position of the object varies with time. Okay, so therefore let's recollect what happened in the last class. After that, we'll move on to the different types of damping, and then we will wind up this class today. Okay, the next class we'll move on to forced oscillations. So look here, what did we do? What did we do were the following. We considered an object to be vibrating. So look here, there was a bucket here. I already drew all the relevant stuff in the last class. So this whole object was vibrating in a container having water, and then there were two kinds of force acting on it. One was there were two force. So when I pull the object and if I leave it, what happens? So there will be two kinds of force that is going to apply on the body. They were restoring force of the spring, and other was the resistive force offered by water for the vibrating body. So if I pull the object in the downward direction, both these forces will act in the opposite direction. Okay, it was clearly I even discussed about how if a parachute falls down, then the atmospheric force will be exerted in the upward direction on the descending parachute. All these things we discussed. So likewise, the resistive force of water will act in a direction opposite to the direction of displacement. Then what did we do? How did we solve? First, you found the resultant force. Then we found the resultant force done. Then the restoring force was given by minus kx. Then the resistive force of the medium was found to be proportional to velocity. Therefore, it was given as minus r into dx by dt. Next, we applied Newton's second law of motion, and we got resultant force was mass into acceleration. That when we plugged into equation 1, we got this equation. So this, if you divide it by mass, so force by mass will give you an equation in terms of acceleration. So the equation in terms of acceleration was this. Okay, and then we introduced two new terms. Those were 2b, which is given by r by m, and omega square, the natural frequency of vibration. We know that it is given as omega square equal to k by m. Okay, then when we plugged it back, the same equation 3 was recasted as what? It was written in terms of b and omega square, which was here, which is present here. Okay, next, in order to solve equation 6, what did we do? We considered that the solution of this equation is going to be of the form, it's going to be an exponential function. Therefore, the solution of that equation is of the form x of t is equal to a into e power alpha t. Next, what did we do? X is known. We found dx by dt. Then we found d square x by d of t square in equation 8 and 9. That when you plugged it in equation 8, that helped us to arrive at an equation called, which was this. Okay, an equation which is this. Okay, this equation when we solved, you see that if you solve this quadratic equation, the solution of this quadratic equation is given by alpha is equal to minus b plus or minus square root of b square minus omega square. How did we arrive at this? This working I will show you in the end of the discussion. Okay, so alpha is this value of alpha. So this has two solutions. One is positive, other is negative. Plus something, plus square root of something, and minus square root of something. This when you plugged into equation 7, that is this, then we arrived at this final equation. What is that given by? Substituting for alpha in equation 7, substituting, look here, where is that? Here. Yeah. So substituting for alpha in equation 7, then the general solution of the equation was given by what? X of t is equal to c into e raised to the power of minus b plus square root of b square minus omega square into t plus d times the second term, which we called it as equation 10. This is clear so far, all of you? What is this? This is nothing but it's just a recapitulation. I mean, we're just recollecting what happened in the previous episode, in the previous class. This is clear, all of you? Abhishek Bhaiya, EC3, is it clear?
Yes, sir.
Okay, then Deepthi Madam, clear?
Yes, sir.
Okay, great. Then Himanshu Shekhar, EC55, clear, man?
Yes, sir.
Okay.
Yes, sir.
Fine. Okay, pa. I think now we will discuss the different types of damping. Before that, what is damping? Damping means if an object is set into vibration, as time lapses, what will happen? The amplitude will decrease and eventually it will come to rest. Okay, that we call it as damping. Okay, so before we discuss the different types of damping, so let me walk through this video. I will show two important videos. One which talks about various types of damping, and the other one will be related to the application of springs when you are shutting down the door automatically. Okay, so therefore that is where the different types of damping plays an important role. Okay, therefore first let us look at this. Okay, look at this video here. Tubelings. Okay, can you see here?
Grammarly does more than catch errors. With Grammarly, you can find really good.
Okay, look here. This is the different types of damping. So in this, I'll just tell you one simple thing. So here what happens is, this is an experimental setup in which you have a scale. So it is just like as though the scale is set into vibration like a simple pendulum. Okay, and what you see here is an iron bar which is attached to it. It is a magnet, and behind that iron bar, what you have? Behind that iron bar, this you can see, no, what I'm showing by cursor. It's an aluminum metal or iron metal. Therefore, what will happen? There will be a magnetic force. So iron, this magnet will attract the iron, or this presence of this magnetic material, it is going to act as a damping force for this medium. Okay, this is clear, no? That's all. And what is being done in this experiment is, they vary the distance between this iron bar and this reference line, that is this distance, and you will see that when this is done, different types of damping are seen. So first let us walk through this, let us observe this video, and then we will discuss the different types of damping. Okay, let me start playing it from the beginning. Okay. All of you watch, pa. Okay, there's a magnet and there is an aluminum block. Did you see here? When the object was set into vibration, it vibrates, and roughly after some 12 oscillations, it comes to rest. As time lapses, the amplitude decreases with time. Eventually, it came to rest. Okay. When the distance between the magnet and aluminum bar happened to be 20 millimeters, that is 2 centimeters. Okay. Next. So here what happened? The body came to rest after some 4 oscillations, after roughly 4 oscillations, 4 or 5 oscillations. Okay. So here what happened? The body performed roughly 1 oscillation and came back to rest immediately. Okay, next see, next observe. So here after 1 oscillation it came to rest. Here what happened? The body that was displaced, it came back to the equilibrium position without doing any oscillation. It just came back. That's it. Okay, which we call it as critical damping. Okay, look here, the body came back to rest without doing any oscillation. No oscillations. Again. So here what happens? The body approaches the equilibrium position slowly. Okay, without performing any oscillation. Yes. Okay, and this is just a collage of different cases. Okay, pa. So is the video informative? Okay. This was one video that illustrates the various types of damping. Okay. They are under damping, over damping, and critical damping. Okay. Now, one more important application of springs. It is with respect to shutting down of doors, automatic shutdown of doors. Okay. That we will see here. Okay. This application of damping in the case of making the door to close automatically.
teenage kids that have a hard time keeping the door closed. Several times I've come home and this door's been open. You wouldn't think so. You think people would close the door. For whatever reason, they're not closing it all the time. So I found a way to fix that. All right, you like to do stuff yourself
Okay.
and save a little bit of
So
money?
look here. So here this person uses a mechanism by which the door can be closed automatically, and this finds a lot of application in library where many students or many people will be opening the door every now and then, frequently, correct, very quite frequently. Then the door, it will automatically close on its own. Okay, and this arrangement of making the door to close open, it is very helpful, particularly in hospitals, then in restrooms, okay, where then in lodges, where in airports, where people will open the door every now and then, very frequently, quite frequent. Okay, in these instances, if this system is put in place, then the doors will automatically close down. Okay, now you see how this person does it by just using a small spring arrangement.
You wouldn't think so. You'd think people would close the door. But in this case, for whatever reason, they're not closing it all the time. So I found a way to fix that. All right, you like to do stuff yourself and save a little bit of money? Well, you've come to the right place because that's what this channel is about. If nothing else, I hope you're at least entertained. I have a lot of how-to videos and do-it-yourself type projects here on the channel, so please take time and look around. Anyways, let's take a look, see what we have for today. So what I have found is this little device right here. And this is a spring-loaded unit. Well, it's actually a spring that is designed to help close the doors. And I'll put a link in the description down below to the Amazon link of where I got this. So if you're interested, you can get one too. And how it works is you pull the center pin of your door and you bring it up, and then this will hook on it. And I'll show you how all that works here in just a second. And then the spring itself helps close the door. So the first thing you got to do is get the pin pulled. Now I've already loosened the pin up, but you'll need like a pick or something that you can put up from underneath and maybe a hammer to tap it. But like I said, I've already got it loosened. So you just want to bring it up a little bit, and basically you want it tall enough that it's going to be above this, so it doesn't, this spring doesn't fall off. So it's going to fit right in between there like that. Then what you got to do is, of course, make sure your door is closed because that's when the spring is least pulled, and you're going to pull this wide open like this carefully because there's a lot of spring tension there, and then you're going to slide it down over the pin like that, and then let one side go, let the other side go, and that's all there is to it. And the only other thing is if you did pull your pin too high, you can use a hammer to tap it down so it's just at the top of the rim here of the spring. So now this is already pushing on the door. So what I'm going to do is go ahead and open the door. We'll keep the camera right on the spring here. You kind of see what's going on here. So basically, it's adding more tension to that spring. And you can't see me right now, but I'm just going to let go of the door. And that spring is going to bring it and close the door. So now if you back up, I'll show you the whole thing from if I were to come in and go out of the door. All right, so let's say I want to go out. You just open the door. And of course, I would step out. I can leave the door, and it closes. It's as simple as that. It doesn't slam hard, and it doesn't really push on you too much when you're trying to do something. It's very easy, so that's good. And so it's not like you have to fight with it, but it's just enough to get that door extra little bit to get closed, so I'm not finding it open. So if you have teenagers that leave the door open, this might be an alternative to you, for you. Well, thanks for taking the time to swing by my channel. I hope you found that video.
So did you find this video interesting? What was done? Simply by just mounting the spring appropriately, you can make the door to shut down automatically whenever it is open. Okay. Now, therefore, now let's walk through the different types of damping. I think I have given ample evidence, ample number of videos on the different types of damping and application of damping wherein you can shut down the door automatically on its own by simply mounting a spring or a suitable restoring force mechanism, by applying suitable restoring force mechanism. Okay. Now look here. Okay, Pa, look here. So what are the different types of damping we have? the different types of damping we have are over damping. Can you see here? 35, for example, 140. What are the different types of damping? The three types of damping are, so they are over damping, under damping, and critical damping. Okay, so the three types of damping are over damping, critical damping, and under damping. Okay, look here, this just depends on the types of damping, how fast the amplitude decays to zero. That is that depends on two factors. One is the choice of value of B. Can you see here? The choice of value of B and the natural frequency of vibration omega. Okay, once again I'll repeat. How many types of damping are there? There are three types of damping, namely over damping, critical damping, and under damping. Okay, so that depends on what? That depends on how the quantity inside the square bracket behave. Okay, in mathematics, in quadratic equation, we call this as discriminant of an equation. Okay, look here. So what are the three types of damping? The three types of damping are over damping, critical damping, and under damping. So that depends on how that depends on the values of B and omega. Values of B means what? It depends on the damping coefficient of the medium. Can you see here? It depends on the damping coefficient of the medium, which is B, and natural frequency of vibration, which is omega. Okay, now what is the condition for over damping? The condition for over damping is B square should be greater than omega square. And what is the condition for critical damping? The condition for critical damping is B square must be equal to omega square. And what is the condition for under damping? Under damping is B square should be less than omega square. Okay, so therefore now let us look at what is over damping. What is over damping? Look here. In the case of over damping, what happens? In the case of over damping, on it. So what is the condition for over damping? Look here. Take paint. Yeah. So what is the condition for what is over damping? Look here. What is over damping? It's my cursor. Yeah, is this. So what is over damping? The condition for over damping is B square should be greater than omega square. In this case, what happens? The body that is displaced from its equilibrium position, it will come back to its mean position quickly and it will not perform any oscillation. Okay, so this is also referred to as dead beat. So the variation of x with t is as shown in the figure 3. Can you see here? This is the figure 3. So in the case of over damping, what happens? That this is the curve corresponding to over damping. Okay, the body will come back to its mean position quickly without performing any oscillation. This is clear. Once again, I'll repeat. What is the definition of over damping? In the case of over damping, the body that is displaced from its equilibrium position will come back to its mean position quickly and will not perform any oscillation. This is also referred to as dead beat. And how you can achieve it? You can achieve it by properly choosing the value of B and omega. Okay, the damping coefficient should be greater than the natural frequency of vibration. Now look here, this is something we call it as tuning. Okay, now look here. When I considered the example of a door that was getting shut down automatically, okay, when I considered the door that was getting getting shut down automatically. Am I right? Look here. Yeah. Can you see here? I don't want to play it. I just want to, yeah. Can you see here? What is preferred? Of course, the door should close automatically on its own. That is there. Okay. Now next question is, how should the door get closed? So if I open the door and leave it, what do you want? There are two possibilities. One is you want the door to close on its own gently and slowly. The other possibility is it will, the moment you leave, it will go and bang with a larger force and quickly. So what you want? What do you want? What do we prefer? The door should close gently, or the door should close with a larger force so that it will hurt everyone. What do you want? What do you prefer? What do we prefer? What kind of shutting of door we prefer? People are here with me. How do you want the door to close? Gently, or you want it to be closed quickly with larger force, so that if someone is before the door, he will also get smashed and he may end up getting fracture. How do you want the door to close?
Gently, sir.
Gently, correct? No? Am I right?
Yes, sir.
Right? Yes or no?
Yes, sir.
Yes.
Yes,
What
sir.
does that mean is we don't want over damping. Okay, clear? So therefore, how you can adjust, or how you can choose the values of B and omega so that the door will close on its own gently, that depends on the choice of B and omega that we make. That depends on the choice of B and omega. Okay, where is my cursor? Yeah, that depends on my choice of B and omega. Therefore, if I choose the value of damping coefficient to be far higher than natural frequency of vibration, it's going to be over damping. The door will quickly close with larger force, by thereby hurting everyone. So therefore, that is not preferred. You got my point? Understood? So by properly choosing the values of B and omega, you can decide whether you want over damping or under damping or critical damping. This is clear? Understood? This is over damping. Simple. What is over damping? B square is greater than omega square. The door will come to equilibrium position quickly and with larger force. That is not preferred. Okay. Next, we'll go to the next type of damping. So what is this critical damping? So what is critical damping? Look here. I'll copy the whole stuff. Okay. Copy. Put it in Paint. Yes. I'll put on top this one. Yeah. Suppose I expand this. Okay. Now look here. I can zoom this down. Okay, pa. I will adjust. Okay. Now look here. What is critical damping? The condition for critical damping is B square should be equal to omega square. Correct? No. In a quadratic equation, when will the two roots be real? If B is equal to, if the discriminant happens to be 0. Correct? No. We say B square equal to 4AC there. Okay. So what is the condition for critical damping? The condition for critical damping is B square should be equal to omega square. So here what happens in this case? In this case, the displaced body will come back to its mean position slowly without performing any oscillations. Someone wants to join? Okay. Once again, I'll repeat. What do you mean by critical damping? The condition for critical damping is B square should be equal to omega square. B square should be equal to omega square. Where is my cursor? Yes. B square should be equal to omega square. In this case, what happens? The body that is displaced from its equilibrium position, it will approach its equilibrium position slowly without performing any oscillation. Okay, clear? Therefore, so what does that mean? What does that mean is, look here. So the body comes back. The body, my mouse is always a problem. Okay, the body comes back. The body will come back to its mean position in a minimum time that is determined by the value of B and omega. B means what? Damping force. Omega means what? Restoring force. Understood? So the body, how quickly the body will come, that depends on the values of B and omega. That is, it depends on the choice of restoring force and the damping force offered by the medium. And how is that? That is shown in figure 3. Okay, can you see in my notes in our file? How does the body come back to its equilibrium position? That is this. If B is equal to omega, it follows this trajectory. Okay, if I copy this, suppose I copy this, copy, then suppose I put it here. Yeah. Okay, can you see here? This curve is what? Critical damping. What is this curve? Over damping. Okay, therefore, how do you want the door to get closed? We want the door to get closed gently, like this, not come and bang with a larger force. So we don't want over damping, we want critical damping. Clear? No? Understood? Is this clear? Okay, that's all. Okay, next is what? Under damping. So what is under damping? Under damping is what we have seen in the first example. Go back. Yes.
There's no place like it. Follow me, Nick Offerman, as I take.
So what is under damping? Under damping is this only. Here what happens? The body that is displaced from its equilibrium position, and if you leave it, what will happen? It will perform some oscillations and eventually it will come to rest. It may be 5 oscillations or it may be 10 oscillations, depends. Okay, let us count here. Okay, this is actually under damping. Okay, yeah, now look here. Okay, now look here, the body is displaced from its equilibrium position when this distance happens to be 20 millimeters or 2 centimeters. Now let us see how many oscillations it will do. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so after some 14 or 15 oscillations, the particle will come to rest. Okay, look here. So there are 3 types of damping. In the case of over damping, what happens? The body comes back to its equilibrium position quickly without doing any oscillation. The case of critical damping, what happens? The body that is displaced will come back to its mean position gently or slowly without performing any oscillation. In the case of over damping, what happens? The body will keep oscillating until its amplitude comes to 0. Understood? So therefore, let us look at the definition of over damping. What is the definition of under damping? That is what you see here. The body oscillates and eventually it comes to rest. Okay, what is under damping? Okay, I think I'll take this, extract this. Okay, let me go to paint. Yeah. Okay, the case of under damping, what happens? I'll remove all the old stuffs. new. Don't save my earlier things. Yeah. Okay, now look here, pa. I think I'll adjust this. So in the case of underdamping, what happens? In the case of underdamping, so the condition for underdamping is, B square should be less than omega square. That is restoring force. The restoring force and resistive force acting on the body are such that the body vibrates with decreasing amplitude. The body vibrates with a decreasing amplitude as the time lapses and eventually comes to rest. Correct? No? Once again, I'll define. So what is underdamping? What is underdamping? What is underdamping? The condition for underdamping is restoring force. The restoring force and resistive force acting on the body are such that the body vibrates with decreasing amplitude, and as time lapses, eventually it will come to rest. So this is given as shown in figure 4. As shown in figure 4 in my diagram is what? It is this. Okay, it is this. Okay, so let me paste it in the same place. Yeah, can you see here? What happens to the amplitude? So the body will vibrate. The body vibrates. Can you see? The body is vibrating. And what happens to its amplitude? Amplitude decreases with the time. Okay, what happens to its amplitude? Amplitude decreases with the time. Can you see here? Amplitude decreases with time. Decreases with time. Okay. So therefore this is, so amplitude is decreasing with the time as shown here. Okay, can you see here the red color curve or white black dotted color curve? Okay, this is about the different types of damping. Okay, so anyone or having any doubts? And what is the importance of underdamping? Sorry, what is the importance of underdamping? Underdamping is particularly useful in, have you seen a tail of a lizard? Have you seen a tail of a lizard? The tail of a lizard, see, look here, for example, imagine that a cat wants to eat a lizard. Okay, so a cat is chasing a lizard. Okay, now what will happen? So the lizard, in order to escape from the cat, from being a victim or a prey, what will happen is, what it will do is, it will shed its tail. Okay, its tail of the tail of the lizard will get detached from its body. Okay, therefore what will happen? There are high chance that the attention of the cat that is chasing this, the attention of the cat that is chasing this lizard will be now on the chopped part of the tail and not on the lizard. By this, what will happen? The lizard will escape and later its tail can be regrown. Okay, now what will happen to the detached part of the lizard's tail? That lizard's tail is going to vibrate for a very long time. Okay, look here, if the detached part of the tail, if it doesn't vibrate, then it is not possible for the lizard to divert the attention of the cat. Understood? No. Therefore, in order to rescue itself in order to rescue or to save its life, what is one of the mechanism that nature has given to it? It can detach the tail, and this tail is going to vibrate, or it is going to wiggle. Wiggle means what? Vibrate. Okay, and how long it can happen? It can happen sometimes for as long as 10 to 20 minutes. Okay, so therefore what do you mean by underdamping? The body is going to perform oscillations even despite the presence of damping force offered by the medium. Therefore, under damping finds an important thing in the wiggling of the tail and it will save its life. Understood? No? Is this clear? Okay. Then one more last part.